Buenas tardes. Good afternoon. Esta sesión va a ser multilingüe, en inglés y en castellano. This session will be multilingual, in English but also in Spanish. So if you need translation, in the outside you can get the device. My name is Josep Puig. I am energy engineer by training, and I have been working since late 70s on energy, both with private companies but also at the university, Autonomous University of Barcelona. And I am in charge to moderate this session. Let me ask at the beginning the two main questions around this session. Is it possible within the urban context to generate the electricity that cities need? What technologies are available today in order to do this, and what will facilitate their development? These are the key questions that we will try to answer in these presentations. The first speaker is Wolfgang Loibl from the Austrian Institute of Technology. Wolfgang has been working for the last 25 years in the AIT, where he is now senior scientist and deputy head of a unit of energy department. His presentation is named Smart Energy Infrastructure, the Research Framework for EERA, Joint Program on Smart Cities. So you have the floor.
Good evening. I have to go to the play button. Okay. Yeah. Good evening. Can you hear me? No, it's better. I was asked to talk about the ERA research network, but I found that the title is somehow misleading because the session deals with something different, so I go more into detail on the other side, but I will have some words on the ERA network. I've divided the lecture into two parts, just the overview of the European Energy Research Alliance, and then I will talk about two projects where quite some people are involved from the era, which are dealing with energy generation, which distributed the energy generation and energy supply also in a distributed way. The area is the European Energy Research Alliance. The objective is quite clear, to make some efforts on new energy technologies. The area has 64 research institutions as partners now, and we have 15 joint programs. If we go back to the questions, then quite some of these programs, you can see them in pink, are dealing with the answers on these questions. Is it possible within the urban context to generate electricity which cities need? The joint program Smart Cities is shown here quite in detail. I just go through regarding energy generation. As every of these sub-programs have a topic in this. Here you find smart grids. You find the building to grid as the issue, and the distributed energy generation as topic for research. And finally, in the sub-program 4, you find solar energy as one main topic. Now I go here back to the projects which are more interesting, I suppose. We have listed here two. One is Transform. Transform shall support smart city development, so any way to support citywide strategies and the implementation of local measures. We shall do some kind of ex-ante assessment of impacts to identify the change in greenhouse gas concentration, in volume of energy consumption, and the changes in energy efficiency in buildings. We have quite some partners. 6 cities are shown here, and quite some partners from scientific and from commercial side. If we go into detail regarding the energy generation, I will here concentrate on solar as energy generation potential. If you do it for a city, what we have done here, then we have to do it by estimating the roof area and to identify which potential is there because of the directions of the roof angles, of the roof size, and to have to identify all the things, and you can then do a calculation on the radiation load for the entire year. This has been done. You can see here a solar potential map of Vienna. This is not only done for Vienna, that there are quite some different cities which have such kind of solutions, but here we have it shown also for the entire city to identify how much distributed energy potential could be gained. And you have here the results as total numbers. You have here that we can somehow identify 4,300 gigawatts, which could be somehow gained and harvested from PV as an installation if we would use all roof area which is somehow suitable for implementation of this. The second project is maybe also quite interesting for you. Here we are dealing with 3 different tools, but not all are dealing with energy. But the second one is quite important because it can deal with energy supply using the distributed as energy generated from PV. During the day, you have usually a problem of consumption, and if you have the possibility to supply cars, for instance, with power from this PV, the installation, this would be quite a solution, but you have to look where these cars come from, how many cars are where, and is there a possibility to have this kind of supply done. We have here 4 cities as partners and quite some other partners from research and from commerce. If you think about how can motion pattern and how can the distribution of population be explored, this has been done here by aggregated mobile phone data. You can identify the anonymized numbers in a way to have it as total for certain areas. The figure you can see here at the bottom this is just a trip summary, and as we are taking these kind of trips to identify the pattern of motion and the occupation of the different areas over time. Here, you can see a visitor volume as electricity supply, which could be a potential to be covered for e-mobility. What you can see at the bottom here, you have here seen for a certain place, which was here, that the numbers of people that are occupying one certain cell, and you can do it for every different cells. So over day, I go here more into detail. Here you can find that we have around 12 o'clock 4,000 people have visiting this certain area. So one can say if you have a model split of 2,000 people, of 50% public transport and 50% of car transport, then you could say, well, there are 2,000 people which have been coming by cars, maybe 1,500 cars could be shown there, so that there's a possibility to supply such a kind in such a number of cars with the PV generated power. This is just a short overview how this can be done, and I think I can give it over to the next people. Thank you for attention, and any questions can be maybe then hold them.
Next speaker is Leonardo Benitez Diez from Indra. Leonardo es director de Smart Energy Indra, es ingeniero eléctrico y tiene un montón de experiencia referente al tema de Smart Energy, y nos va a exponer una ponencia que es How Smart Grids Technology Supports the New Paradigms of Smart Cities.
Gracias. Thank you. So I think I'll try to do it in English. Good afternoon. My presentation will try to respond to this first question, how we can generate more electricity in cities, but mainly focusing on the grid, because in the end, I have seen the colleague that speak before me and the ones that will speak later will probably tell you what are the technologies that can be used in a city to generate, but in the end that generation should come into the grid, and the grid is what it is now and is what we foresee in the future. But it's very important to consider the grid in any of these plans. We have to put solar panels in every roof. That's fine, but you need to send that energy into the network, and you need to manage that, and you need to keep the stability in that network. So I'll try to answer or try to give you my vision on what are the technologies needed to be able to do that. No? So first of all, I'm trying here to bring these two words together, smart cities and smart grids, which mean a lot of things, each one of them, and at the same time they are very much interconnected. No? So here just bringing some topics to the table. First of all is that smart cities, to be smart, need to install or to deploy some platforms, some technologies like the one that appear there. Distributed generation is what we will be talking this afternoon. Electric vehicles, that topic was touched also by my colleague before. Energy efficiency systems, the idea that the clients, that the consumers are able to act on the demand, to make decisions on the demand. Smart public lighting, smart heating systems, that's another topic related to smart cities, and the ability in the future to have, or in the present, but in the future everybody thinks that storage will be something real, and that there will be the capabilities to store energy in the city, of course, in every house or in public spaces. So all this is very much tied to energy. For all this, you need electricity, and you need a grid, a good grid working and delivering the service. No? On the other side, the companies, the utilities. So this is the vision from smart city, from the utilities. The utilities are also deploying massively smart meters, as you know, because of regulatory, because the regulation is imposing that, and at the same time because they need to give better service to the clients. No? So both worlds are, in a way, as it says there, feeding back each other. No? and we have to see how that can be managed. No? In this second slide, I'm bringing here the challenges for utilities. The challenges for utilities, as it says there, energy is smart cities depend a lot on energy to support the functions that were described before, and a smart grid should ensure the following objectives. No? The remote monitoring of network facilities, allowing the automation of diagnosis and operations, the secure and reliable integration of distributed generation, as it was mentioned before, the safe management of the electric vehicle recharge infrastructure, and the interaction with home energy management systems in order for the end users, for the citizens to be able to interact to make decisions on the consumption of energy. And this leads us to a very basic problem that utilities have right now. And the very basic problem is that up to now, utilities have been basically blind after the medium voltage network. So basically, they were monitoring the medium voltage head at the exit of the substation, the primary substation. So basically, they had a telecontrol point there. They were bringing that data through the SCADA to the control center, and that's it. They didn't have much information of what was going on after the exit of the medium voltage line. Basically, they were blind in terms of the low voltage, the secondary substation, etc. So the whole idea behind smart grid is be able to give visibility to that and be able to interact and be able to use that information to make decisions, operation decisions. And it's not because it's nice to have, it's because it's needed if smart cities, if we want to incorporate all these services into the smart cities. If you don't have this, it will be impossible to integrate renewables, it will be impossible to integrate car recharging infrastructure, it will be impossible to give all these services we want to give to the citizens. No? So with the new smart meters that are being deployed globally, at least in Europe, in North America, the same happens in some countries. There are plans in some countries in Latin America, in Africa, or in Asia. The idea of making visible that demand. And that means installation of smart meters, installation of communications to the smart meter, being able to bring that information online in real time to the control center of a utility. At the same time, the capability that we have now to incorporate sensors in the network, not only in the demand, also sensors in the secondary substation, sensors along the medium voltage line, along the low voltage line, that will give us the possibility to monitor technical losses, to detect potential frauds or non-technical losses, collection of grid data to be able to feed the distribution management system, or what is called ADMS, Advanced Distribution Management System, and the ability to interact with the consumption. Up to now, the consumption was basically passive. So everybody consumes the power needed whenever they want. I mean, there was no action in the demand was passive. In the future, everybody is foreseeing that the demand will be able to make decisions on when to consume energy, when to turn on the machines at the home, when, of course, the electric vehicle has a lot to do with the idea of recharging the electric vehicle during the night when the load is low and when the price of the energy is less costly. You know? So all this needs technology and needs, and again, all this is working on a network that needs to be balanced in real time. I mean, the storage of energy is still something that everybody thinks will happen in the future, but right now, that is not something that we can count on. The grid needs to be stable and needs to be balanced on a real-time basis. So next slide, if it comes, is how we foresee the future. You can see there at the left a typical control center where you are basically managing all these substations, primary substations, the exit of the medium voltage exit, and you have the wall, the video wall at the back. You have the operator there with the SCADA, with a DMS. But basically what you can operate is on the medium voltage network, on the primary substation. The idea is that in the future you will need to operate down the lines in low voltage and in the medium voltage. So in the future we are seeing the need to have what we call medium voltage, low voltage control centers, which are these things that appear at the right. No? So you will have, maybe in a city, you will have one or more than one medium voltage, low voltage control center that is managing a certain piece of a network. Because again, you have massive amount of information you have to manage, you have new tools available, you have the ability to distribute the intelligence, and you have the capacity to act on new elements, not only in the exit of the substation. You can act on many areas, even in the demand. Okay. I will not get into detail because I only have 3 minutes left, but this is our concept of what can be a medium voltage, low voltage network operation, the technology that can be there. Basically, we are foreseeing a real-time bus that has the ability to interact, to connect to all these devices in the network. We are foreseeing a CEP engine, an engine that allows you to automatically detect patterns, automatically solve problems, what we call auto-healing in smart grid, and up the ability to have analysis, diagnosis, real-time management, outage management, and also demand management. So the idea of, again, what is the change? The change is that you need to manage a lot of information coming from the smart cities that everybody is envisioning and that we are seeing here in this event. For that, we are, as Indra, we have worked in a real-time platform that appears there that we think is the future, the way to manage all this information. On one side is based on a real-time bus, that is the first point, that is able to connect to all these devices, to SCADA systems, and to different head-ends in the field. It's based on a unified data service with the ability to manage standards and be able to connect to different applications. It has a CEP engine embedded where you can manage, where you can automate certain algorithms and be able to detect problems and do some self-healing. And at the same time, the ability to persist the data in what is called big data, meaning databases that are meant for big amount of information and not the relational databases that we see now. The last slides, I only have 1 minute. There are 3 or 4 slides here to showing some projects that we are working here in Spain. One of them is Nemocoded and Imponet, where we are working on the smart metering side. Another one is 3 Houses, that is a European project where we tested technology for energy efficiency in different countries in Europe. This is ARROWHEAD. This is a project we are doing here in Barcelona and in the Basque Country, where we are also interacting this smart grid platform with a smart city platform, and we are also doing a demonstrator. And the last project is PRICE. This is a project that is close to Madrid in the Henares Corridor, where we are working in 3 packages, and this is a smart grid project where we are testing all this technology, and also the slide at the figure at the bottom is the platform we are implementing for demand management. The idea of the ability of the demand, of sending price signals to the demand, and being able to act on the demand using all this technology I mentioned before. So that's it. I think I passed some seconds, and so it's fine. So in the end, if there is any question, I will be here.
Thank you, Leonardo. The next presentation is from Lara Pérez and Marcel Macarulla. Lara is an engineer specialized on energy and environment. She integrated the GNARUM renewable services team as project manager for European projects. And Marcel is from the UPC, the Group of Construction Research and Innovation, and he's working currently on the Encourage project, which is the title of his presentation.
Okay, hello. We'll try to make the presentation in English, even if the The slides are in Spanish. So we are presenting a European project called Encourage. It's a 3 years project which will end next year. With here you see the countries and the companies and institutions working on it. It's an Artemis-financed project, and the name is Encourage, which means Embedded Intelligent Controls for Buildings with Renewable Generation and Storage. So this means here in this picture we can see more or less the context of what we are talking about. We have in one side the demand, so the consumption in buildings, in neighborhoods, so not only one building but different buildings. Then we may have some supply, some distributed generation, photovoltaics, wind, CHP or something else. We have the network, the utilities. We may have some storage. And what we have to do is to know what we are going to produce. So we need to make a generation forecast. We need to know what we are going to consume, so a load forecast, and then we put everything together in an energy management system so that we can take some decisions on what strategies we may implement. If we want to sell to the grid at one moment, or we want to sell to another building which may need some energy at that moment, or we want to stop some loads which may not need that much energy at that time, and so on. So with this project, we're trying to answer some of the main challenges that we have with energy optimization in buildings. First, as here we are talking about renewable energy, so renewable energy is very variable, and it's difficult to know when we are going to have some energy or not. So this is an important challenge we have to deal with, so we have to make some predictions there. We also, to optimize, we need to reduce the consumption, otherwise we won't be able to balance local production with consumption. So we will have to make a huge analysis of the consumption patterns to optimize it. And for this, we may need to analyze a huge quantity of data that can come from a SCADA or something like that, and it's very complex to analyze from a person cannot understand a lot of data. So we need to deal with that. And another important, interesting thing is that what is good for one building may not be the good thing for a whole neighborhood. So in this project, we try to make a brokerage between different buildings, so to buy and sell one building to another. So this is a picture of the architecture that we have implemented, but here the important thing is the middleware, which we have tried to make very that can understand many languages, because this is another challenge that different vendors use different protocols, and we have to understand everything. So we have built here a gateway with a middleware to ensure interoperability, and then we have developed the supervisory control, who does all these algorithms to know which strategies we are going to implement. And then we have the energy brokerage and business intelligence modules that deal with forecasting or with analysis of data, or to decide whether we sell some energy to another building. So the prediction is very important in this context. We have developed a prediction of loads based on neural networks. When we do that, we also have the possibility of analyzing the baselines of the consumption patterns and already see some things that we can do better. So Marcel will talk about that later. Then we also need the prediction forecasting. For this, we have used the GWise solution from GNARUM that can predict what the renewable energy plants are going to produce, even in small scale, which was the challenge in this project, because it's easier to make a prediction for large plants, but it's more difficult to make it in small scale distributed generation plants. And then we have an important part, which is the business intelligence module, that has to transform data, raw data like this, which are not understandable by a human being, into something like that, which is easier to understand. So we have made a huge work building cubes that is transforming the data into n-dimensional cubes that you can analyze and give you at the end KPIs that you will be able to understand as a person. So we have obtained a dashboard like that the energy manager will be looking at and deciding strategies that not the machine but a person can implement. So Marcel is going to explain how we have made the demonstrator of this project in the UPC.
Okay, good afternoon. Well, here you can see a screenshot of our dashboard. The most important thing here is that we have to define different KPIs. Well, which is the importance of that KPIs? For example, if we want to calculate the savings of our building, it's not possible to do it. We know which was the energy consumption from the last year. We know the energy consumption of this year, but the conditions, the external conditions could be different. For example, the time, the weather, the occupancy of the building. For this reason, it's important, or there's a lot of work to define these KPIs. These KPIs are used also to detect different potential investments that the energy managers can do or can carry out in the building. Okay, I will explain briefly the UPC demonstrator. In the UPC demonstrator, we have 3 types of building: lecturer apartment, students' hall of residence, and finally, the one academic building. I will focus my presentation on this last building, the academic building, because I don't have a lot of time. What we've done in this demonstrator is to monitorize one room of each type. We monitorized one lecturer room, one computer room, and finally one office, one lecturer's office. We analyzed these different rooms through the dashboards, and we obtained some conclusions. In each room, we monitorized the energy consumption, the temperature, the humidity, and the occupancy and other parameters. Well, using these algorithms that Lara showed you, we find that we can apply different strategies to reduce the energy consumption. For example, we can reduce the energy consumption in the different rooms only switching off the lights or switching off the energy when nobody is in the room. For example, in the PC rooms, we can reduce the energy 35%. If we extrapolate these savings in the whole building, we can say that we can reduce 6% of the energy. If we do the same in the class and in the lecture room, we can reduce 10% the energy consumption. Extrapolating this savings in the whole building, we can reduce the energy consumption 2%. And finally, if we do the same in the lecturer's office, we can reduce the energy consumption 120%, and extrapolating these numbers in the whole building, we can reduce 2.5%. Another strategy that we are testing is the optimization of the use of the PC rooms. We are trying to force the different users to use the computers that are near the windows during the day, and during the night or where the light is not enough and we have to turn out the lights, we are forcing the users to move to those computers that are far from the windows. This is just to assure that we are using the computers for equal. And finally, we are taking, for me, an important actions that is user awareness. We accomplished 9% of reduction. And finally, we are studying different other algorithms, such as turning on and off the lights of the corridors and acting in the heat pump. Sorry. Okay. Here you have our contact data, and if you have any questions at the end, we will answer you the questions.
Thank you, Lara and Marcel. The next speaker is Carlos Merino. Viene del Centro Nacional del Hidrógeno y es manager de Power Electronics y Control Division del Centro Nacional del Hidrógeno. Nos hablará de una experiencia con almacenamiento de hidrógeno a partir de renovables.
Eso es. Buenas tardes a todos. Mi presentación va a ser en inglés, perdón, en español. Y bueno, espero que ya siendo la última hora de la tarde de la jornada, pues aún nos queden fuerzas. Bueno, ya avanzaba sobre los resultados o el proyecto que queremos presentaros. Está relacionado con el almacenamiento de energía en forma de hidrógeno acoplado a lo que son microredes. De una manera muy rápida, presentar la organización de la que vengo, que es el Centro Nacional del Hidrógeno, y que es una instalación científico-técnica singular. Es la categoría o la nomenclatura que recibe a nivel español, y que es una infraestructura para apoyo a la investigación y también apoyo al sector empresarial. Intenta actuar de bisagra entre estos dos mundos que en ocasiones no se ponen de acuerdo o no hablan el mismo idioma. Y nuestro objetivo es testear, validar prototipos y equipamiento, desarrollar y escalar procesos y certificar y verificar componentes. El resultado, de una visión muy rápida de lo que os presento esta tarde, es el resultado del desarrollo de un proyecto que se llama el proyecto GEBE. Fue un proyecto desarrollado con otras empresas y centros de investigación y que cuya temática era microredes y smart grid, y en la que se construyeron o se instalaron distintos demostradores a nivel nacional en distintas geografías. El objetivo de este proyecto era el diseño, la construcción de estos demostradores, que cada uno tenía unas particularidades o unas diferencias que lo hacían pues singulares. En el caso del Centro Nacional del Hidrógeno, nosotros aportamos a este proyecto pues la posibilidad de un almacenamiento de energía en forma de hidrógeno. Esta instalación, que es una plataforma experimental, se encuentra actualmente en funcionamiento en nuestras instalaciones en Puertollano, y lo que aglutina es pues tanto energías renovables como almacenamiento de energía, y todo ello pues para dar servicio a una serie de cargas. Bueno, aquí podemos ver un gráfico, una pequeña representación, un esquema de esta microred, que más adelante iremos describiendo, pero es una microred que de momento es una microred aislada, interconectada en un bus de corriente continua. Nosotros y el hidrógeno, bueno, pues se postula como uno de los sistemas de almacenamiento de energía y evidentemente no es el único, es uno más, ¿no? Lo que sí que permite es dar respuesta a todas las escalas de almacenamiento de energía, tanto a la escala pequeña como a los grandes sistemas de almacenamiento. Y esto es cada vez más necesario y es donde están centrados pues, muchos aspectos en investigación de lo que son los sistemas de almacenamiento de energía. Sobre todo, puesto que las energías renovables cada vez más se empiezan a integrar dentro de la red y empiezan a tener pues, mayor importancia, y estamos tratando con generadores de energía eléctrica que son generadores no despachables. Esto bueno, ya lo conocen todos ustedes. El recurso renovable, pues en la mayoría de los casos, hay en ocasiones que sí, pero en la mayoría de los casos es no gestionable. El sol sale cuando sale y el viento sopla cuando sopla. Y nosotros como consumidores pues tenemos unos patrones muy concretos de consumo, tanto a nivel doméstico como a nivel industrial, y que es rara ocasión en la que estos patrones de consumo coinciden plenamente con los patrones de generación. Por eso es necesario contar con sistemas de almacenamiento de energía. Y el proyecto, la instalación que nosotros tenemos, cuenta con sistemas de energía fotovoltaica de 3 kilovatios pico instalados sobre una cubierta, con la posibilidad de cambiar la inclinación para maximizar la energía. Tiene un pequeño minero generador de 800 vatios y evidentemente, como estamos trabajando con sistemas de energías renovables, pues una recogida de datos mediante una sencilla estación meteorológica. La parte de almacenamiento de energía, puesto que ya avanzaba antes, es una microred que se encuentra aislada, es muy importante contar con estos sistemas de almacenamiento. Se lleva a cabo mediante dos tecnologías distintas. Una tecnología que sería la convencional o que habitualmente se instala, que sería tecnología en almacenamiento en baterías electroquímicas, y un almacenamiento en forma de ciclo de hidrógeno. El ciclo de hidrógeno, el hidrógeno como tal, pues no existe en la naturaleza y es necesario producirlo, y hay diferentes tecnologías de producción de hidrógeno, y nosotros hemos optado en este caso por la electrólisis alcalina, que se alimenta la electrólisis polimérica, que se alimenta de energía eléctrica, para posteriormente pues llevarlo a un sistema de almacenamiento en gas comprimido, y posteriormente, cuando fuese necesario volver esa energía a la red, pues se haría esa transformación mediante una pila de combustible, que en este caso es una tecnología polimérica también, de 1 kilovatio. Hemos descrito las fuentes que tenemos energéticas, los sistemas de almacenamiento, y ahora todo esto es con un objetivo claro, y es dar respuesta pues, a unas determinadas cargas que tenemos conectadas a esta microred. Tenemos dos cargas diferenciadas. Una carga que serían cargas domésticas, las habituales que podemos encontrar en una pequeña vivienda y que son los electrodomésticos pues, más comunes, que se encuentran a su vez controlados pues, por un sistema domótico, en este caso era muy sencillo, con un protocolo domótico X10. Y también adicionalmente tenemos un sistema, un punto de recarga de vehículo eléctrico, que podríamos decir que es muy peculiar, puesto que se alimenta de un bus de corriente continua y que tiene la posibilidad de dar servicio a un vehículo eléctrico a partir de energía no solamente de renovables, sino de energía procedente del hidrógeno. Podemos ver en cada uno de los gráficos de qué estamos hablando, de las cargas domésticas, y esto sería la pantalla que a modo de usuario, pues en el punto de recarga del vehículo eléctrico, recoge los principales parámetros de esa recarga, ¿no? De la energía, el porcentaje o de dónde proviene la energía que está utilizándose en ese momento para recargar el vehículo eléctrico. Y bueno, como somos un sistema que estamos aislados de red y solamente nos abastecemos de energías renovables, pues evidentemente es energía renovable 100%. y por eso estamos monitorizando o calculando cuáles serían las emisiones de CO2 evitadas a la atmósfera y a su vez también los euros ahorrados, puesto que la utilización que hemos abierto, la utilización de este punto de recarga, que es de uso público, la hacemos de manera gratuita. Para poder, una vez presentados pues, los componentes de la microred, para poder conectarlos y operarlos adecuadamente, pues es necesario utilizar distintos tipos de capas, y así se habla en microredes, y podemos tener pues, la capa eléctrica y la capa química, y más adelante pues, veremos la capa de control. Ya avanzaba antes, ¿no? La capa eléctrica, en que consistía, es la interconexión de estos generadores que por su cercanía y por el nivel de tensión elegido, que es de 24 voltios, es adecuado para aplicaciones que podrían ser en entornos rurales, allá donde no hay posibilidad de conexión a la red, y también posibilita sistemas de autoconsumo pues, aislados de red que den servicio. Adicionalmente tenemos un sistema de interconexión en el lado del ciclo de hidrógeno, un sistema de gestión de los gases generados, y bueno, pues para todo ello pues hace falta una serie de instalaciones que tanto cuenten con toda la monitorización y toda la gestión en electroválvulas que son necesarios para controlar el sistema. Algo muy importante, una vez que está implementado este laboratorio, por así decirlo, esta solución de Smart Grid, es evidentemente lo que sería el control asociado a esta microred. Para poder hacer un control óptimo de la microred, primero fue necesario pues, crear modelos matemáticos que reproduzcan el comportamiento de cada uno de los generadores, de las cargas y, en definitiva, de todos los elementos conectados a esta microred. Y para ello se desarrollaron los modelos de simulación necesarios con el objetivo de, antes de llegar a las pruebas en campo, encontrar estrategias óptimas que den servicio y que cumplan con los requisitos que podemos fijar en cada momento. Y estos requisitos podrán ser tanto técnicos como, si determinamos, también económicos. Adicionalmente, una vez realizada esta simulación, pues es necesario realizar un sistema de control, un sistema SCADA, que recoja todas las variables y las monitorice y que a su vez nos permita pues, esa recolección de datos de la instalación para su posterior análisis. Y evidentemente esto debe estar gestionado por un sistema que puede ser un sistema distribuido, con una inteligencia distribuida, puesto que cada uno de los equipos se controla de manera autónoma. Y adicionalmente hay un PLC maestro en el que se implementan pues, las estrategias de control para cada uno de los casos. Y bueno, podemos ver los modelos que han sido desarrollados, y en el caso del SCADA, este sería el SCADA de ingeniería, y también fue desarrollado pues, un SCADA más a nivel doméstico o usuario, en el que se recoja la principal información, la información más importante, de dónde está proveniendo cómo está funcionando la microred. Y bueno, este era el trabajo que quería presentarles, y bueno, si tienen alguna pregunta, pues al final o bueno, pues ahora, encantado de responderles.